Welcome to the deep dive. Today, we're going to try to give you a whole new appreciation for something I bet you use every single day, but probably don't think too much about: the internet.
Right.
Specifically, the networks that make up the internet and the language computers use to communicate across those networks.
Yeah.
I've got some excerpts here from two German instructional texts on basic network operation. They're actually from a distance learning program.
Oh, wow.
And we're going to use them kind of as a jumping off point for our deep dive today.
Yeah, it is fascinating how we just take the internet for granted these days.
Right.
But, understanding the nuts and bolts can really change your perspective on things. It's like learning a secret code that unlocks this whole hidden world.
That's a great way to put it. We're going to cover a lot of ground today, but our main goal is to give you a solid understanding of some core concepts. We'll unpack how IP addresses work, we'll demystify the roles of those little boxes we call routers and switches, and we'll uncover the systems that make connecting to websites as easy as typing in a name.
Right.
By the end of this deep dive, you'll have a much clearer picture of how the internet actually works.
Hopefully. It all starts with communication.
Okay.
How devices talk to each other on a network.
And these instructional texts start by introducing the OSI model to break it all down.
Yeah.
I like to think of it as a blueprint for network communication, kind of like those exploded diagrams you see in an instruction manual.
Oh, that's a great analogy.
Yeah.
The OSI model divides network communication into 7 distinct layers.
Okay.
Each layer handles a specific part of the process, from the physical transmission of data over wires or radio waves, all the way up to the applications we use to interact with the internet, like email and web browsers.
Okay, so we've got these 7 layers, but in the real world, things are a bit messier, right?
Oh, yeah.
Like, how does this theoretical model actually translate into the systems we use every day?
That's where the TCP/IP protocol suite comes in.
Okay.
Think of it as a streamlined version of the OSI model that's actually implemented in the networks we use. While it doesn't follow the 7 layers exactly, it embodies the same principles of breaking down complex tasks into manageable chunks.
Got it.
Okay.
So the OSI model is the conceptual framework, and TCP/IP is the real-world implementation.
Right.
Now let's zoom in on a crucial element of network communication: IP addresses.
Okay.
What are they and why are they so important?
Think of an IP address as a device's unique identifier on a network, like a home address in the digital world. Just like you need a specific address to send a letter, your computer needs an IP address to send data to another device.
Right, and these texts focus on IPv4 addresses, which are probably the ones you're most familiar with.
Right.
They're those sets of 4 numbers separated by dots,
Right.
like 192.168.1.1.
Yep.
But what do those numbers actually mean?
Those numbers aren't random at all. Each IPv4 address is actually a 32-bit number, but we represent it using that dotted decimal notation for human readability.
Okay.
Each of those 4 numbers, called octets, represents 8 bits of the address.
Okay, so there's a method to the madness.
Yes.
But how does this actually help devices communicate?
Each IP address actually has 2 main parts.
Okay.
The network ID and the host ID.
Okay.
The network ID is like a street name, identifying the network a device belongs to, while the host ID is like a house number, identifying the specific device within that network.
So it's like saying this data is going to house number 10 on Elm Street.
Right.
But how do computers know which part of the IP address is the street name and which part is the house number?
That's where subnet masks come in.
Okay.
They're like a key that unlocks the structure of the IP address.
Hmm.
The subnet mask tells the computer which bits of the IP address represent the network ID and which bits represent the host ID.
Okay, so the subnet mask is essential for decoding the IP address. But what if I want to send data to someone who's not on my same street, so to speak?
Right.
That's when routers come into play.
That's right. Routers are the crucial link between different networks.
Okay.
Think of them as post offices that sort and forward mail between cities. If you're sending a letter to someone in another town, it first goes to your local post office,
Right.
which then directs it to the correct post office in the recipient's town.
So if I'm emailing my friend across town,
Yeah.
my computer first figures out we're on different networks. Then it sends the data to my router, which uses its own address book to figure out the best way to get that data to my friend's network and eventually to their computer.
Exactly. And that address book for routers is called a routing table.
Okay.
It contains information about all the networks the router knows how to reach and the best paths to get there.
Gotcha.
This ensures that data gets to its destination efficiently.
This is already making me look at my router a little differently. But before we get too deep into routing, there's one more thing I want to unpack. How do computers figure out if two devices are on the same network in the first place? The texts mention something called the A-ending procedure.
Right, the ending procedure is how a computer logically compares IP addresses to see if they belong to the same network. It involves a bitwise A&D operation between the IP address and the subnet mask.
Okay.
And then comparing the results.
Okay, I'm going to need a bit more explanation on that one.
Sure.
Can you give us a real-world example of how this A-ending thing works?
Imagine you have a letter with a full address, but you only want to know if it's going to the same zip code as you.
Okay.
You'd essentially be masking out all the other parts of the address and just focusing on the zip code.
Okay.
The ending procedure does something similar with IP addresses,
Gotcha.
masking out the host ID and only comparing the network ID.
That makes more sense.
Yeah,
So if the network IDs match, the devices are on the same network and can communicate directly. But if they don't match, then the data needs to be routed to a different network.
precisely. And that's where the magic of routing really comes into play.
Right.
But before we get into that, let's take a step back and consider this. Remembering a bunch of numbers like 192.168.1.1 isn't exactly user-friendly, is it?
Definitely not. I can barely remember my own phone number, let alone a string of random numbers for every website I visit.
That's where DNS comes in, the domain name system. It's essentially the internet's phone book.
Okay.
It translates human-readable domain names like google.com into those numerical IP addresses that computers understand.
So when I type google.com into my browser, DNS is working behind the scenes to look up Google's IP address, so my computer knows where to send my request.
Exactly. It's a hierarchical system that starts from the root and goes down to top-level domains like .com or .org, then to second-level domains and so on.
Okay.
Your computer sends out DNS queries, like asking what's the IP address for google.com, and the DNS servers respond with the answer.
That's way more convenient than having to memorize IP addresses for every website.
Oh, absolutely.
But we haven't talked about one more piece of this puzzle that's crucial for getting connected to a network in the first place, DHCP.
Right. DHCP, or Dynamic Host Configuration Protocol, is like an automated welcome committee for devices joining a network.
Okay.
Imagine having to manually configure the IP address and other network settings for every new device.
Yeah, that sounds like a nightmare.
It would be a nightmare.
Yeah.
DHCP takes care of all that automatically.
Okay.
It's like a concierge that assigns a temporary IP address and other network settings to a device when it connects.
Okay.
This makes connecting to a network as simple as plugging in your Ethernet cable or joining a Wi-Fi network.
So when I connect to my home Wi-Fi, my laptop essentially shouts out, hey, I need an IP address.
Oh, hey.
And the DHCP server responds with, okay, here's one, along with all the other information you need to get online.
That's a great way to put it. And the beauty of DHCP is that it manages IP addresses efficiently. If a device disconnects, its IP address goes back into the pool for other devices to use.
Gotcha.
This is especially important for large networks, with many devices connecting and disconnecting frequently.
Okay, we've covered a lot of ground already. We've explored the OSI model, dived into IP addresses and subnet masks, learned how routers connect different networks, and uncovered the magic of DNS and DHCP.
We have.
But there's one more elephant in the room we need to address. IPv4 addresses are running out.
That's right. The internet has grown exponentially,
Yeah.
and we're quickly running out of those familiar IPv4 addresses.
Right.
That's why the transition to IPv6 is so important.
Okay, and that's exactly what we'll be diving into in the next part of our deep dive.
Looking forward to it.
Welcome back to the deep dive. Last time we talked about how IPv4 addresses are running out.
Right.
And it really got me thinking about all the devices we have connected these days.
Yeah.
Not just computers and phones, but smart TVs, security cameras.
Oh, yeah.
Even refrigerators. It
Yeah.
seems like everything needs an IP address these days.
It's true. The Internet of Things is exploding, and we're rapidly approaching a point where IPv4 just can't keep up.
Right.
That's why the transition to IPv6 is so important.
Okay, so last time we learned that IPv6 uses 128-bit addresses instead of the 32 bits used in IPv4.
That's right.
That's a huge increase in address space, but I have to admit those long strings of hexadecimal numbers can be a bit intimidating.
Yeah.
How do we even make sense of them?
It's actually not as complicated as it might seem.
Okay.
Instead of those familiar dotted decimals,
Right.
IPv6 uses a combination of hexadecimal numbers and colons.
Okay.
Each group of 4 hexadecimal digits represents 16 bits of the address.
Gotcha.
And those groups are separated by colons.
Oh.
So a typical IPv6 address might look something like 2001.0db8.858.80000000.0367334.
Okay, I'm starting to see the pattern, but are those numbers still divided into network and host portions like IPv4 addresses?
Absolutely. The leftmost bits of the address typically identify the network, while the rightmost bits identify the specific interface or device on that network.
So it's still the same basic idea. You need a way to identify both the network and the specific device within that network.
Right.
But the texts mention that IPv6 doesn't use traditional subnet masks.
That's right.
How does that work?
Instead of subnet masks, IPv6 uses a slash notation to indicate the length of the network prefix.
Okay.
For example, a 64 prefix means that the first 64 bits of the address identify the network, leaving the remaining 64 bits for interface identifiers.
Ah, so it's a more streamlined way of representing the same concept. But, with all these extra bits, doesn't that make subnetting even more complicated in IPv6?
Actually, it's quite the opposite.
Oh.
The larger address space in IPv6 makes subnetting much more flexible and manageable. With 64 bits for interface identifiers, you can have a massive number of devices on a single subnet without worrying about running out of addresses.
That makes sense. So it's not just about having more addresses overall, but also about making network management easier. Now, the instructional texts also mention something called link local addressing.
Right.
What's the purpose of that?
Link local addresses are used for communication between devices on the same local network segment without needing a globally routable IP address. Think of it like having a separate internal address system within your home network.
So if my laptop and my printer are both connected to my home Wi-Fi, they can talk to each other directly using link local addresses, even if my internet connection is down.
Exactly. These addresses are automatically configured and always start with V80, followed by a colon, and then the device's interface identifier.
That's pretty handy. The text also mentioned that link local addresses were initially designed to be derived from the MASI address of the network interface card, but that raised some privacy concerns.
It did.
Can you elaborate on that?
Sure. MP addresses are unique identifiers assigned to network interface cards.
Okay.
And the idea was to leverage that existing uniqueness for link local addresses. However, this approach meant that a device's link local address would remain the same across different networks, potentially allowing for tracking of devices.
Ah, so someone could potentially track my laptop as I move between different Wi-Fi networks if they knew my MSC address.
That was the concern.
Right.
To address this, modern operating systems now use privacy extensions that generate randomized interface identifiers for link local addresses, making it much harder to track devices.
That's good to know. So IPv6 has built-in privacy features to prevent that kind of tracking.
It does.
Now, one of the things that really impressed me about IPv6 is this concept of stateless address auto-configuration, or SLAC.
Yeah.
It sounds like magic.
It kind of is.
Devices just automatically configure their own IP addresses.
It is pretty amazing. SLAC is a key feature of IPv6 that simplifies network administration and reduces the reliance on DHCP servers.
But how does it actually work? How does a device magically know what its IP address should be?
It's a multi-step process. First, the device generates a link local address, as we discussed earlier. Then it sends out special messages called router solicitations to discover routers on the network.
So it's like the device is shouting, "Hey, any routers out there? I need some information."
Exactly. The routers respond with router advertisements, which contain information about the network prefix and other configuration parameters. The device then combines this information with its own unique interface identifier to create a globally routable IPv6 address.
Wow, that's pretty clever. It's like a self-service system for IP addresses. But what about situations where we need more control over IP address assignments? Does DHCP still have a role to play in the IPv6 world?
Yes, it does. While SLAC is great for basic configuration, DHCP v6 provides more advanced features. It allows administrators to assign specific IP addresses to certain devices, configure DNS servers, and manage lease times for addresses.
So it's like having the option to either let the system automatically handle things or to step in and manually configure things as needed.
Right.
But what about all the devices and systems that still use IPv4? How do we manage this transition to IPv6 without breaking the internet?
That's a great question, and it's one of the biggest challenges of IPv6 adoption.
Yeah.
The texts mention several transition mechanisms designed to bridge the gap between IPv4 and IPv6.
Okay.
One of them is called dual stack.
Dual stack. Does that mean running both IPv4 and IPv6 simultaneously?
You got it. Dual stack allows devices and networks to support both protocols,
Okay.
enabling communication with both IPv4 and IPv6 systems. It's like having two phone lines, one for landlines and one for mobile phones.
So it's a way to ensure backward compatibility while gradually transitioning to IPv6. But what about situations where you have a device that only supports IPv6 trying to communicate with a device that only supports IPv4? The text mentions something called tunneling for those cases.
Right. Tunneling is a clever technique that involves encapsulating IPv6 packets inside IPv4 packets,
Okay.
allowing them to travel across parts of the internet that only support IPv4. It's like putting a letter inside another envelope with a different address.
So the outer envelope has the IPv4 address,
Yeah.
which is understood by older routers.
Right.
And once it reaches a part of the network that supports IPv6, the inner envelope with the IPv6 address is revealed.
Exactly. This allows IPv6 traffic to reach its destination, even if the entire path isn't fully IPv6 enabled.
Gotcha.
The texts mention specific tunneling mechanisms like 6-4 and Teredo, which are designed for different scenarios.
Okay, so there are different tools and techniques for managing this transition. It sounds like a complex process, but it's good to know that there are solutions in place. But, it's interesting to think about the implications of IPv6 beyond just having more addresses. What other advantages does it bring to the table?
One of the key benefits of IPv6 is enhanced security. IPv6 has built-in support for IPsec, a security protocol that provides authentication and encryption for IP traffic. This helps protect against eavesdropping, tampering, and data breaches.
So it's like having a built-in security system for your network traffic.
Right.
That's a significant advantage over IPv4, where security is often an add-on.
Absolutely. Another advantage of IPv6 is simplified network configuration.
Okay.
With features like SLA-EC and more efficient address allocation, managing IPv6 networks can be significantly easier than managing IPv4 networks, especially for large organizations.
It sounds like IPv6 is designed to address many of the limitations and challenges of IPv4.
It is.
But I'm curious, what are some of the obstacles to wider adoption of IPv6? If it's so great, why haven't we all switched over yet?
That's a good question. One of the biggest challenges is inertia.
Okay.
There's a huge installed base of devices and systems that rely on IPv4.
Right.
And transitioning those systems can be costly and time-consuming. There's also a lack of awareness and understanding of IPv6 among many IT professionals and users.
So it's a bit of a chicken and egg problem.
Yeah.
People are hesitant to switch to IPv6 because there isn't enough support for it.
Right.
There isn't enough support for it because people haven't switched over yet.
That's a good way to put it.
Yeah.
But despite the challenges, the transition to IPv6 is inevitable. The internet is evolving.
Right.
And IPv6 is the foundation for that evolution.
Okay, so we've gone from deciphering those hexadecimal numbers to understanding the benefits of IPv6 and even some of the challenges of adoption.
We have.
But there's one piece of the puzzle we haven't talked about yet. Routing.
Ah, yes.
How does all this data actually get from point A to point B across the vast network of the internet?
That's where routing comes in. It's the brains of the internet, the system that makes sure data packets find their way to their destinations.
Right.
And that's what we'll be exploring the next part of our deep dive.
Welcome back to the deep dive. We've been unpacking the fundamentals of computer networking, and now it's time to tackle a topic that's both crucial and, I'll be honest, a little mind-boggling to me, routing.
Yeah, it can be a bit complex, but it's really fascinating once you start to understand how it works.
So far, we've talked about IP addresses as a kind of digital home address for devices.
Right.
But how do those packets of data actually find their way through the maze of networks that make up the internet? I mean, it's not like there's a single postman who knows the entire map of the internet.
You're exactly right. It's not a centralized system at all.
Okay.
It's a distributed system that relies on millions of interconnected devices called routers. Think of routers as traffic junctions. Each router has a routing table that tells it where to send data packets based on their destination IP addresses.
So it's like each router has a local map of the internet?
Right.
And they work together to guide data packets to their final destination.
Exactly. When a router receives a data packet, it looks up the destination IP address in its routing table. If it knows the direct path to the destination network, it sends the packet on its way.
But what if the router doesn't know the direct path? Does it just give up?
No, not at all. If the router doesn't have a direct route, it forwards the packet to another router that might have a better route.
Okay.
This process continues until the packet reaches its destination. It's a bit like asking for directions. You might need to ask several people before you find someone who knows the way.
Okay, so routers work together to create these pathways for data. But how do they actually learn about the best routes in the first place? The instructional texts mention something called dynamic routing.
Right. Dynamic routing is how routers learn about the best paths.
Okay.
It's a process where routers exchange information about the networks they're connected to and the routes they know about. They use special protocols like RIP and OSPF to share this information and keep their routing tables up to date.
So it's like a constant conversation between routers where they're sharing gossip about the best ways to reach different destinations.
That's a great analogy. And just like gossip, routing information can spread quickly through the network,
Yeah.
allowing routers to adapt to changes in network conditions and find the most efficient paths.
This dynamic routing thing seems pretty sophisticated,
It is.
but the texts also mention something called static routing. What's the difference?
Static routing is a bit more, static.
Okay.
It's like giving a router specific directions that don't change. It's a manual process where a network administrator configures a router with a fixed path to a particular destination.
So if I always want traffic destined for a specific server to go through a particular router for security reasons, I could use static routing to enforce that.
Exactly. Static routing can be useful in situations where you need more control over traffic flow
Okay.
or when you have specific security or performance requirements.
Okay, so we've got dynamic routing, where routers learn from each other,
Right.
and static routing, where we give them specific instructions. But with all these routers and routes, it seems like things could get pretty complicated.
Definitely.
Is there a way to see the path a data packet takes across the internet?
There is. You can use a tool called traceroute.
Traceroute.
Yeah, it allows you to send a test packet to a destination
Okay.
and see the list of routers it passes through along the way.
So it's like dropping breadcrumbs along a path
Right?
and then following them to see where you've been.
Exactly. Traceroute can be a valuable tool for troubleshooting network connectivity issues, identifying bottlenecks, and understanding how traffic flows across the internet.
This whole deep dive has been a fascinating journey for me.
Yeah, me too.
We've gone from understanding how computers on the same network communicate
Right.
to exploring the complexities of routing across the vast internet.
It's amazing how much goes on behind the scenes, isn't it?
It really is. It's all happening without us even realizing it every time we send an email, browse a website, or stream a video.
It's a testament to human ingenuity and the power of collaboration that we've built this intricate system that connects billions of people around the world.
It really makes you appreciate the internet on a whole new level, doesn't it? I have to admit, I'm a little overwhelmed by all this information.
It's a lot to take in.
It's amazing to think about all the complex processes that happen in the blink of an eye just to make the internet work.
It is remarkable.
Yeah.
But I hope this deep dive has given you a new appreciation for the invisible world of computer networking.
It definitely has.
The next time you connect online, take a moment to think about all the routers, switches, protocols, and algorithms working tirelessly to make it all possible.
I definitely will. Thanks for guiding us through this deep dive.
It was my pleasure.
It's been an eye-opening experience. And to our listeners, thanks for joining us. Until next time, keep exploring, keep learning, and keep diving deep.